Greetings, sir. This is Muazz, and along with my team, I'll be presenting for our theory digital assignment. And the problem that we have tried to tackle is the traveling salesman problem. Our team number is team 4, and in my team, I have me, Mohammed Zuberi, Gauri Gupta, Shravan Prakash, Sai Aravind, and Raswanth. So we have chosen to tackle the traveling salesman problem, and these are the points that we will be covering throughout our presentation. We will be introducing the problem first of all, then we will be discussing its implementation with the brute force approach. After that, we will be discussing its implementation by the greedy approach, then the dynamic programming approach, and then we will be comparing the time complexities of all these approaches. So first of all, what even is the traveling salesman problem? The traveling salesman problem is a basic algorithmic problem that in which we have to find the shortest path for a salesman who has to travel to different cities. There are different paths to these cities, so we have to make sure that the salesman has the least amount of distance to travel when he is traveling throughout the different cities. We have to make sure that he travels all the points that are given, all the cities that are given, and that should be covered in the least amount of distance. Okay, so there are different approaches to tackle this problem, and we have tried to discuss three. That is the brute force approach, then the greedy approach, and then the dynamic programming approach. So the first one will be discussed by Gauri.
The brute force approach is a guaranteed way to find the correct solution by listing all the possible candidate solutions for the problem and is ideal for solving small and simpler problems. This is how we solve the traveling salesman problem using brute force approach. In the function main, we take input of the number of cities by the user and then create an adjacency matrix initialized to 0. We then take the distance matrix as input. Then we call the function salesman to compute the shortest path and pass the adjacency matrix, the number of nodes, and the sources arguments. In the function salesman, we use a loop and store all vertex apart from the source vertex in a vector. We generate all the n-1 factorial permutations of cities using a while loop and calculate the cost of every permutation and keep a track of the minimum cost permutation. This function returns the cost of the permutation with minimum cost, which is then outputted in the main function. The time complexity of the algorithm is dependent upon the number of nodes. If the number of nodes is n, then the time complexity will be proportional to n factorial, in this case, O(n) factorial. The most amount of space in this graph algorithm is taken by the adjacent matrix, which is an n cross n two-dimensional matrix, where n is the number of nodes. Hence, the space complexity is O(n) square.
Now we will be running the problem. See, I have inputted the number of cities. Then I input the distance matrix. I have it copied in my notepad. So I'll just copy paste that. And now we'll be running the code. So the minimum distance as it's stated here is 80, and we can verify it as well. This is the correct answer. The second problem that we will be discussing about is the greedy approach. In the greedy approach, what we do basically is first of all, the greedy approach is used in many algorithms such as Kruskal's algorithm, Prim's algorithm, and Dijkstra algorithm as well. It's a simple approach in which we compare the distances of different points, and we just update those points based on the distance. If there is a distance that is large, then we just update it with the lower distance. If there we find a distance or a path that is shorter than that, we just replace it with that path. And that is what we have tried to do here in our solution as well. This is the code for the traveling salesman problem with greedy approach. In the int main, we have taken input for the number of cities and the number of the distance matrix as we had done in the previous problem itself. Then we have just made for loops and while loops to run the code. We have also traversed the adjacency matrix. Then we have made conditions for the corners of the matrix as well. We have also checked the path. First of all, we have started from the city 0, as stated here. Okay, it's the 0th index city, and we have taken that as our first city, and we have run the code in that way. Okay, then we have also updated the cities as we found that some distance was shorter. We have also updated the path, and that is what we have tried to do here. I'll also run the code to show that to you here. as I'll take the same inputs as in the previous problem just to verify if both the answers are same and if both the code is working correctly as well. So in the previous problem as well, I had 4 number of cities, and I'll copy paste the same like adjacency matrix here, and I'll run the code. So the minimum cost here as well is 80, and in the previous problem as well, if we can say the minimum distance was 80. So here we see that both the problems, both the approaches give us the same answer. So both of them are correct. Now we'll be moving on to the third approach, that is the dynamic programming approach.
The dynamic programming approach is generally used to reduce a complex problem into many variables with a series of optimization problems with one variable in every stage. This is how we solve the traveling salesman problem using dynamic programming approach. In the main function, we take input of the number of cities by the user and then create a subset of 2 to the power n. We create two vectors, one to store the distance matrix and one to store the subset subdistance. We then take the distance matrix as input. We call the function build subsets, which generates the minimum subdistance for each ending city in each possible subset. We start with the shortest possible tour, starting and ending at the first city, and iterate all subsets that include the first city with size greater than 2. Then iterate through ending cities excluding the first city and find the minimum subdistance for this subtour with j as ending city. We call the function min cycle, which searches for the shortest Hamiltonian cycle. Backtracking starts with subset that contains all the cities. We mark first city as visited, find next non-visited city with best subdistance from previous city in the cycle, mark city as visited and excluded from the subset. We then print the shortest path from source to vertex and the shortest distance. In the dynamic algorithm for TSP, the number of possible subsets are n cross 2 ki power n. Each subset can be solved in O ki power n times. Therefore, the time complexity of this algorithm is O n square cross 2 ki power n. The dynamic programming solution uses a table of size O star 2 ki power n. The notation O star means that we ignored the polynomial factors.
Okay, so now we'll be running the code for this as well. The number of cities, as we had done in the previous two examples, would be same, that is 4. And the distance matrix will also be the same. We'll input the same distance matrix. And see, we also get the shortest path in this problem, in this solution. And we also get the shortest distance, that is more important, and that is also 80. That is common to both the previous solutions as well. So hence it is verified, all the 3 solutions give us the same answer and all of them are right. Okay, now we'll be continuing with our presentation. So the next thing that we'll be talking about is the time complexity and the comparison of these 3 approaches. For the brute force, as Gauri like herself mentioned, the time complexity for brute force is O to the power O n factorial. Okay, the time complexity for greedy algorithm is n square, that n square multiplied by log base 2 n, and the time complexity for dynamic programming approach is O n square 2 to the power n. These are the 3 time complexities. If we have a simpler, like if we have a very simple problem, then it is preferred to go ahead with the brute force approach. But if we have a complicated problem, it is recommended to go ahead with the dynamic programming approach. Okay, now we'll be looking at the application of this algorithm and the whole traveling salesman problem.
Real-life application of a traveling salesman problem can be seen in mobile applications such as Google Maps. Like if we want to go to 5 places, so the map will tell you the shortest possible path, passing through all the 5 places. So with this, we come to an end of a presentation. This was our team. You can see the names of the team members on the screen. Thank you for giving us this opportunity, sir. We learned a lot about the traveling salesman problem and a lot more things. Thank you.